And I think it's time to already start with the first presenter, which is Professor Alessio Vecchio, which I am personally a bit connected because he was one of my professors. And particularly was my professor during the PhD. And he's a professor at the Dipartimento di Ingegneria dell'Informazione, Vice President of the Computer Engineering and Artificial Intelligence and Data Engineering programs. His research activity concerns network measurement and pervasive mobile computing. His research interests also include bioinformatics. He's also a researcher at the CNR, which is the National Research Council of Italy, member of the Pervasive and Computer Network Laboratory. He served as one of the organizing and technical program committee of several international conferences. He co-founded the IEEE PerMobi workshop. So Alessio, buongiorno, welcome, and the stage is yours.
Hello, everybody. Thank you, Massimo, for the nice introduction. And also I would like to thank Elisa for giving me the opportunity to present our research here at LACNIC. It's a real pleasure. We'll start sharing my screen. Okay. So the topic of this first presentation is the energy consumption of application and transport level protocols from the point of view of client devices. So the scenario that we consider is made of Internet of Things devices that are connected via cellular access and communicate with a server possibly located in the cloud. And what we would like to understand if there are any differences, especially in terms of energy consumption when using different protocols. In particular, we focus on transport level protocols like QUIC and the more classical TCP/TLS. So here we have the outline of the presentation. So we will start with a simple model of the energy consumption of 4G cellular interfaces, and also which is the setup that we used for measuring the energy consumption of devices. Then we have two case studies. The first one is about the three different versions of the HTTP protocol. The second case study is about the MQTT protocol, again analyzed when using QUIC and TCP, and then we will conclude. Okay, so let's start with the energy model of 4G interfaces. It's a simplified model, the one we can see right now. But the idea is, whenever the interface has something to be transmitted or received, it will be in the continuous reception state that requires the maximum amount of power. Then, if the system remains silent for a time equal to Tc, then the interface will move to the short DRX state that is more energy efficient compared to the continuous reception one. Then, if the system remains again silent for a time equal to Ts, the system will move to long DRX, to the long discontinuous reception state that is even more efficient compared to short DRX.
Y luego, si el sistema se mantiene silente por un tiempo igual a L,
whenever there is something to be transmitted or received, the interface will move back to the initial CR state, and then it will move accordingly to the same criteria. In short DRX and in long DRX, the system is able to save some energy because the interface is turned on and off quickly, and this saves some energy. The only difference, let's say, between short DRX and long DRX is the duty cycle that in long DRX saves a greater amount of energy. Here we can see the power consumption of the interface in the different states. As we can see, in continuous reception, the amount of power needed is approximately 1,000 milliwatt. It is much lower in short DRX, even lower in long DRX, and the minimum value, 14 milliwatts, is the one that is obtained in the idle state. Now, these values can be different from interface to interface, and also the time to move from one state to another one, let's say, is subject to some configuration from the mobile network operator. Okay, this is the setup that we use for measuring the energy consumption. We like measurements, so we adopted an experimental approach. We used some power monitors that are able to measure the amount of current that is needed by client devices. And there is a controlling PC that allows us to repeat the experiments as needed. The advantage of this approach is that the energy consumption that we measure is the real one. It is also accurate. Obviously, there are also some drawbacks, in particular that experiments are limited to laboratory sessions. As you can imagine, it's rather difficult to carry all this stuff around. Okay, let's move to the first case study, where we consider different versions of the HTTP protocol, and in particular because we wanted to understand which is the behavior from the point of view of energy of the HTTP 3 version that is now based on QUIC. On the contrary, HTTP 1.1 and HTTP 2 are based on the more classical TCP transport protocol. In particular, QUIC provides some nice mechanisms, like it integrates security since the beginning. It is possible to multiplex and demultiplex streams on the same connection, and also the connection setup is generally linear compared to TCP. Okay, the communication model that we analyzed is very simple. Communication is periodic, so the client sends HTTP requests to the server side. It will receive a reply, and then it will sleep until it is time to start again. Okay, this periodic model is typical of many machine-to-machine scenarios. For the client side, we used both single-board computers, in particular Raspberry Pis, and also smartphones. And for the server side, instead, we used services provided by Cloudflare, in particular Cloudflare Workers, and also the Google Cloud Storage. We also explored different distances from the client, which was located in Italy. In particular, we used some facilities in the United States and also in Australia, as you can see. Okay, this is a logical view of the experimental setup. So there is a controlling PC that controls the power monitors. The power monitors are connected to the smartphone and the Raspberry Pi. Those devices send their requests to the server. using cellular access and then going through the public internet. There is a small difference in the setup we use for the Raspberry Pi compared to the smartphone. In particular, for the Raspberry Pi, we also used this, let's say, additional channel that is basically UART connection that allows to transfer some information from the Raspberry Pi to the controlling PC. And we used this mechanism to put some timestamps into the power trace. And this is useful because it allows us to measure the energy needed for every single request response cycle. In terms of client-side software, we used Carl plus some libraries for being able to use HTTP3. And for the smartphone, we used the OK HTTP library plus Cronnet. Okay, this is an overview of the set of experiments that we carried out. As I mentioned, we used Cloudflare, in particular Cloudflare workers. We implemented a simple HTTP echo service. So the client sent some information to the server side, and the server side sent this information back to the client side. We explored a somehow limited number of payloads because running these experiments took a bit of time. And the only facility that we used is the one in Milan, so in Italy. For the Google Cloud Storage service, we only used HTTP GET requests, so communication is now asymmetrical. We have been able to explore a larger set of payloads, and also the set of facilities that we explored is larger. So again, Milan, and then a facility in the United States, and the last one in Australia. The experiments for the smartphone are basically the same. The only difference is that it is not possible to evaluate the energy consumption of every single request-response cycle. So we took the energy consumption in longer periods, and then we averaged the observed amount. The three protocols have been used in a random order to avoid any bias coming from the specific order they have been used. And this is the results that we obtained for the smartphone Cloudflare scenario. The yellow line is the energy consumption of HTTP3. The other two lines is the energy consumption of HTTP 1.1 and HTTP 2. And what we can see is that the energy consumption of HTTP 3 is generally higher than the other two versions. We also applied some statistical techniques that say that the difference we can see is statistically significant. This is the set of results of the smartphone Google Cloud Storage scenario. In this case, there are no clear differences. I mean, there are some differences, but they are small. These are real experiments. This would be just some random noise or slightly different network conditions. And in this case, the statistical test didn't provide any evidence of differences. This is the single board computer, the Raspberry Pi and Cloudflare scenario. Also in this case, HTTP3, the yellow line, needs more energy compared to the previous versions of the protocol. Again, this difference is statistically significant, and also the results are more accurate because, as I mentioned, in this case, we are able to measure the energy needed by every single request. Obviously, as it happens also for the previous results, when the payload is increased, also the energy consumption increases, And this is obvious. This is somehow obvious because we are transferring more information. Okay, and this is the set of results for the Raspberry Pi Google Cloud Storage experiment. In this case, for small payloads, it's not clearly visible here because the picture is somehow small, but for small payloads, HTTP3 provides some benefits in terms of energy consumption. So it needs less energy than HTTP1 and HTTP2, and the same more or less applies also for the other facilities. But when the payload becomes larger, in general, HTTP3 needs more energy compared to the other two versions of the HTTP protocol. We also carried out some additional experiments using a 4G, 5G interface. And we also, let's say, updated our curl version. In particular, we at the beginning evaluated the possible differences between curl 7.85 and curl 8.2.1. So basically a more mature implementation of the QUIC protocol. And what we observed is that the more mature implementation provides some benefits in terms of energy consumption. As you can see, for the more recent versions of curl, the energy is lower compared to the previous version. These results have been obtained in a different configuration compared to the previous one. So we used just 1 megabyte payloads, GET requests, and the web server we used was the Caddy web server executed in the facilities of the University of Pisa. Okay, here we have other results that have been obtained with the same setup, using the more recent version of curl. And we also introduced some additional delay using TC-NetM, and this is the amount of additional delay that we introduced. And the results show that for small payloads, HTTP3 can be better than HTTP2. Let's consider this graph where the payload is 128 bytes. And let's focus on these two box plots. The red one is HTTP3, the blue one is HTTP2. And what we can see is that HTTP3 saves some energy. And the same applies also here, 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 and here, when the delay is artificially increased. And more or less the same also applies when the 5G connection is used. For larger messages instead, what happens is the opposite, as we can see in the last graph, okay, that is related to 4 megabytes payloads. And in particular, we can see that in general, HTTP3 needs more energy compared to HTTP2. Okay, and this concludes the first case study, and let's move to the second one that is based on another application level protocol that is MQTT. It is a publish subscribe protocol that is used for resource constrained devices. It can run on top of TCP/TLS and also QUIC. The idea is that clients that are interested in receiving some information can subscribe to a broker. In this example, we suppose that they are subscribing for temperature information. And then when another client operating as the publisher will send some temperature values to the broker will take care of forwarding this information to all the subscribers. In this case, we also adopted another metric, that is the age of information. The idea was to also measure something more, not only energy. In particular, the age of information is useful because it provides a measure of the data freshness. Okay. The age of information can be defined as the current time t minus the timestamp of the freshest data that we received. Okay. Now, given this definition, the age of information has a typical sawtooth shape, and the reason is, let's suppose that at this time we received a packet containing some fresh data, and then we are not receiving any new information, so the age of information increases until a new packet is received right now, and the age of information drops to this value. Then it starts increasing again until a new message is received, it drops, and then it will grow again, and so on. And the reason why it does not go to zero here is because of the network latency. Okay, so when this information is received on the subscriber side, it has been produced some time ago. So basically, this is the impact of network latency. Now, if we focus on the average age of information, and we consider also the message rate, okay, there is a typical curve that can be observed, this one. So let's start with increasing the message rate. What happens is that the average age of information gets better. Okay? And it gets better because we are sending more frequently fresh information. But at a given message rate, the system starts being overloaded. Okay? And sending more messages worsens the age of information. So in this part of the curve, the age of information gets higher simply because some queues are formed in the client, in the network, in the broker. So we are not getting any benefit by sending messages with a higher rate. We adopted an experimental setup that is quite similar to the previous one. So there is a publisher that is basically a Raspberry Pi. It is connected to the public internet via cellular access. There is a broker that is executed within the network of the University of Pisa, and a subscriber that is, again, in the same local area network. And information goes from the client to the broker, and then from the broker to the subscriber. We executed a number of experiments, and we considered, let's say, 3 possible solutions at the transport level. The possible solutions are QUIC, TCP-TLS, and also TCP-TLS with the Nagel algorithm disabled. We considered this set of possible rates for the generation of messages, and the payload size was rather small, just 128 bytes. In this case, we used an MQTT client that we built by ourselves. We just used the Queen Rust implementation of the QUIC protocol, and we also used version 1.3 of TLS. And we didn't rely on any segment offloading capability at the kernel level because it was not supported for the Raspberry Pi and cellular interface that we used. And this is the result that we obtained in terms of freshness of information, the age of information. What we can see is that QUIC, the blue line, provides better results compared to the standard TCP-TLS, that is the orange line, the orange curve, but simply disabling the Nagel algorithm in TCP provides much better results. That is the green curve that we can see. For all of them, the edge of information gets lower because of what we saw before. This is the part of the curve where increasing the message rate provides some benefits. And we measured at the same time also the energy consumption of the three possible solutions. The standard TCP-TLS is the best one in terms of energy efficiency. That is the orange curve. TCP-TLS with the Nagel algorithm disabled is the second most efficient solution in terms of energy, and the most energy demanding solution is QUIC, at least in this part of the message rate space, because for higher message rates, as you can see, the green and blue lines intersect. Okay, but now we would like to have the best solution, both in terms of energy consumption and age of information. Okay, this is a multi-objective optimization problem, and let's suppose that these are possible solutions. Okay, here we have the age of information, and on the other axis we have the amount of power needed. And a solution is Pareto optimal when an improvement in one objective requires a degradation in the other. Let's consider, for instance, this solution. Okay, this is Pareto optimal because if we need a better age of information that this solution provides, we need to increase the power consumption. We can't have a better solution according to both energy and data freshness. There is also a set of results, let's say, that are basically useless and they can be discarded because they are not efficient. Let's consider, for instance, this solution, okay, and this one. This one has a better energy consumption and a better age of information, so this one can be simply discarded and not considered anymore. And here we can see the three Pareto fronts for the considered solutions. So the blue belt is QUIC, the green belt is TCP-TLS with the Nagel algorithm disabled, and the yellow-orange belt is instead the standard TCP-TLS with the Nagel algorithm turned on. And what we can see is that in general, the green solution, TCP-TLS with the Nagel algorithm disabled, provides more efficient results compared to QUIC, both in terms of energy consumption and age of information. We have to consider that all these solutions are somehow optimal. Then if you are interested in having very little energy consumption, we are going to look at these solutions. If you are interested in having a better age of information, we are going to look at this set of solutions. But most of the time, the green solutions are better than the blue one. The belts are somehow overlapped because the difference is not so large, and we also repeated the experiments a number of times. And there is also a part of the solution space where TLS with the Nagel algorithm turned on provides, let's say, better results. Okay, let's move to the conclusions. What we can say is that there are large differences in terms of energy consumption between the quick and more traditional protocols. So it makes sense to evaluate both of them. The maturity of quick implementation significantly affects the energy consumption, as we saw for the more recent version of the Cool tool. And also seems that the interaction between quick implementations can be important in terms of energy efficiency. Sometimes quick is better than TCP/TLS. When it happens, this is mostly for small payloads, but for larger payloads, it is generally the opposite. And another important result is that aggregation provides large benefits in terms of energy consumption. For instance, when we use the Nagel algorithm, there is aggressive aggregation. This provides much better energy consumption, but at the same time, it will increase the age of information. So the data we receive is, let's say, less fresh. Overall, quick can be better than the default TCP/TLS, but simply by turning off the Nagel algorithm provides equal or even better results. There are also some limitations that we have to consider. We evaluated protocol implementations. There are many other implementations of quick. They are also getting better every month. And also the client side is somehow not particularly heterogeneous, so it would make sense also to increase the devices on the client side. I would also like to thank all these people because they've been participating in producing these results. And there is also a draft paper of the MQTT results that is available on the archive. And I finished. If you have any questions, I will be pleased to answer.
Thank you, Alessio. Thank you very much for the very interesting presentation. I invite everyone now to ask questions to Professor Alessio in the mics in the room or through the Q&A panel on the Zoom platform. Massimo, do we have any questions in the room?
Can I ask one question? Quick question.
Yeah, please.
Yeah. So, did you find like what's the reason behind why Quick is more energy consuming for the high or larger payloads?
I think there are multiple reasons. It is somehow a little bit more demanding in terms of computational power needed. It is executed in the user space compared to TCP. And for some of the setups that we used, for instance, the generic segment of loading that, let's say, transfers some of this work to the kernel space was not available. And possibly this has an impact also in terms of energy consumption for the platform we considered. Another point is probably the different aggregation level they have. We would like to study this a bit more thoroughly, but I think that they have different aggregation factors, let's say, and in the end, this also plays a role in the energy consumption. And another point could also be just the different timings they have, because it's not only the amount of data that we transfer using the cellular interface, it is also the time between when a packet is sent and the next one is sent or received. They also the timings play a role, and probably also this timing being different has an impact in terms of energy consumption. And also probably implementations are not as mature as they are for TCP. So we can possibly expect some improvements in the next future.
Okay, thank you. Thanks so much for your presentation.
I have another question for you, Professor. Your results about HTTP are based on a regular communication pattern. Do you also have results for other traffic models, for example, more similar to browsing?
Yeah, we considered that simple traffic model because it makes sense for machine-to-machine communication. That is basically the scenario that we consider as the most interesting one for the energy consumption point of view. But we also have some limited results for, maybe I can share my screen. I have probably. I have some extra slides that I didn't use. Yeah, this one. We carried out a simple experiment where communication is more browsing-like. So there is a first HTTP request and then other requests for downloading the objects included in the web page corresponding to the first request. And what we observed that in this case, HTTP3 seems to behave much better than in the regular periodic communication pattern that we saw before. We can also see that in general, parallelism in terms of transferring more objects has a positive impact in terms of energy consumption. We can see that when parallelism is 1, the amount of energy needed is this one. And then when we use higher level of parallelism, let's say 5, the amount of energy that is spent for downloading the same information gets lower.
Thank you, Professor, for your answer.
Thank you for sharing. Thank you.